Okay, so let's begin. In number 1, the question is number 1 up to 10 are MCQ questions. So in number 1, it's a basic acceleration question. You have to find the acceleration. You're provided with the final velocity, the initial velocity, and the distance moved. You have to find the acceleration. So we use this formula to find the acceleration. It comes to negative 25 squared by 40. In the question they asked you, give the magnitude of the car's deceleration, just the value, not the sign. So the value is 25 squared by 40. That's what we wrote. Question number 2, an object is falling through the air. So they're asking us how much energy is dissipated by air resistance. So whenever something is falling from the air from a height, it has GPE, gravitational potential energy. So as it falls, the GPE gets converted into kinetic energy as well as thermal energy, which is lost to the air resistance. So we have to find the thermal energy only. So we subtract the kinetic energy from the GPE. That will give us the energy dissipated by air resistance. So GPE minus KE. GPE was 8.2 into G is 9.81 and height was 25. Minus half mv square is going to give us the kinetic energy, half into 8.2 into 20 square. That's what we got here. Okay, let's move on to question number 3. So here you're seeing an acceleration time graph, and we can see that the acceleration time graph, it's showing that the acceleration is increasing. So if acceleration is increasing, we have to use the velocity time graphs to see in which of these graphs the acceleration is actually increasing. So in A and B, we can see that the gradients, because the gradient of a velocity time graph gives us acceleration, we can see in both A and B that the gradients are decreasing. That means in both A and B, it's actually deceleration. And in C, because the gradient is constant, that means it's a constant acceleration. But in here, we can see that the acceleration is increasing. That means the gradient cannot be constant. The gradient has to be increasing as well, because the acceleration increasing means the gradient of the velocity time graph has to increase as well. So that is why D is the only possible answer for this one. Then number 4, if we wish to find the gradient from a graph, we have to basically make use of this equation. S is equal to ut plus half at square. From this one, if we say that the object is falling from rest, as they have told over here, the object is falling from rest. So that means u would be 0. And if u is 0, that means this equation becomes half at square. But in this place, the a is actually the acceleration due to gravity, which is g. So if I wish to find g from this equation, we get 2s by t square. So if I plot a graph of 2s against t square, 2s on the y-axis and t square on the x-axis, I'm going to get the gradient, and that gradient is going to give me the value of g. So that is why this is the answer. A student is investigating a material in the form of a wire. Which of the following properties will change if a longer wire is used? So out of these 4, breaking stress, density, and the Young modulus, all of these 3 factors, they actually depend on the material itself. So they don't actually depend on anything else except the material type. Okay, so just like, glass has a different breaking stress, density, or Young modulus, similarly rubber has a different breaking stress, density, and Young modulus. So the only thing that can change if a longer wire is used, it has to be the stiffness. In number 6, it's a basic momentum collision problem. So here they're telling us we have to find the total momentum after the collision, sorry. So the momentum before the collision we can find using the information. So object A's mass is 2 and object A's velocity is 3 meters per second to the right. So if we take the right to be positive and the left to be negative, so the momentum of A would be 2 multiplied by 3 positive, plus the momentum of B would be 5 multiplied by minus 2, because we are taking the left to be minus. So we get how much? Minus 4 kg meters per second to the right. So basically after the momentum, the collision would be the same as before the momentum, because we have to make sure that the law of conservation of momentum is maintained. So whatever momentum we got before the collision would be the same momentum after the collision. We got minus 4 kg meters per second to the right. Okay, to the right it's minus 4 kg meters per second. Why? Because this thing over here, if we added them, this momentum to the left is actually more than the momentum to the right. That is why we got a negative value. So that means negative momentum to the right means is actually momentum to the left. So that is why this is the answer. Number 7, this is a basically falling through, a ball is falling through oil. So in here, the weight would become equal to the addition of the upthrust and the drag force. So if we wish to actually find the terminal velocity at V, between V and W, it hasn't even reached the oil. Between W and X, it has just started to flow through the oil. So if we wish to actually find the terminal velocity, it has to be found within X and Y, within this huge range so that we can get a proper value. Okay, and by the time it reaches y and z, it's actually reached terminal velocity. So if we wish to find the actual value of terminal velocity, we have to find this between x and y. That is why x and y is the answer. Then which of the following is a vector quantity? Of course momentum, because only this one has, you know, direction out of all of these. Then number 9, which doesn't is not correct for Newton's third law pair forces. So third law pair forces, of course, they act in opposite directions, action and reaction. They're of the same time, of course. They have the same value as well. The only thing that's incorrect here is they act on the same body. We know that whenever Newton's third law pair forces act, if object A provides a force to object B provides a force to object A in the opposite direction. So actually the forces act on two different objects. The last one of the MCQ questions, they're asking us to find the time taken, and they have provided us with you know, information related to find the work and the time, and the power is already given. So work is force multiplied by distance. Force is given and distance is also given, so we multiply them and we make sure that the SI units are maintained. Kilo means 1000, so 10 to the power 3, and 1 kilometer means 1000 meters. So we maintain the SI units and we're going to get the answer properly. And the next one is this one. We now move on to the broad questions. Number 11 is about moment. So if we look carefully in here, we have to label the forces. So we can see this person here, according to the question, has a weight of 650, so we label it from the center of gravity of the person. This person has a weight of 950, so we label it from the center of gravity of the person. We always have to make sure that the weight is labeled from the center of gravity. And they've also told us that the uniform plank, this plank is uniform, meaning its weight acts from exactly its center. So if it's 4 meters long, the weight is going to act from 2 meters. Weight is 250 newtons. It's provided in the question. So we wrote it. And then using principle of moments, we found the value of x. And basically the point to be noted is the main trick part is over here. I mean, where the distance from the, where the, you know, weight of the plank is actually acting from the, you know, pivot. So it's here, and you have to basically, to find the distance from the pivot, you have to subtract 0.90 from 2, because this much is 2. Out of this 2, 0.90 goes over here. So you have to basically subtract 2 minus 0.90. Okay, so this is what you have to basically keep in mind. Next one is number 12. So in number 12, they are asking us to find the rate at which the passenger does work. So rate of work done is basically power, right? Rate of work done is power. So power is what? Force multiplied by velocity. So force is given. Force is basically the, you know, weight of the person. So weight of the person is what? Mass into g. Okay. So because the person is getting lifted upwards, the weight is acting, of course, downwards. It doesn't matter if the person is going upwards or, you know, standing still, the weight will always act downwards, right? So m into g gives us the weight, and the velocity of the person is mentioned here, but it's important to understand that the elevator is taking him at an angle of 30 degrees to the horizontal, right? Lifting up at an angle of 30 degrees to the horizontal. So we have to take the vertical component of the, what can I say? The vertical component of the speed, right? So the vertical component of speed is actually 0.51 sine 30. So you have to take that because the person is going upwards. So we have to take the vertical component, because work done is always force multiplied by distance moved in the direction of the force. So we have to take the distance in the direction of the force, which is vertical. That's what we did. And our answer came to 180 watts, which is approximately 200 watts. Then number B is a question where the efficiency has been mentioned, and they have said, calculate the power input when 15 passengers of the average mass 72. So the average mass 72 was the same mass that was given for the first person. So 15 such passengers of such mass, we have to find the power input necessary to be provided by the provided to the elevator. Sorry. So the power output we can find, of course. Power output is, it's here, 180 is for one person. So for 15 people, it would be 15 multiplied by 180. And then we use the formula for efficiency, which is efficiency is equal to useful power output by power input. From here we can find the power input, which comes to this one. Then number 13, a rugby player is basically kicking a ball, as we can see, and they're asking us show that the initial velocity of the ball is about 17 meters per second. So in here the information that we are provided with is this is u, we don't know it, so let's take it as u, the initial velocity, and because the ball has been kicked vertically upwards, so we have to take the vertical component of the velocity, which is u sine 35. and then we know that when it reaches the highest point, the maximum height, it stops, right? Whenever something reaches its maximum height, it actually stops. So it stops here, v0, and it moves 5 meters from the ground. So s is 5, and acceleration would be minus 9.81 because it's acting against gravity. So from here we can find the value of u, which comes to 7.3, and that shows actually that it's approximately 17. So we got our question properly solved. Then in this one, they are basically discussing whether it will be a score or not, whether it will be a goal or not in the rugby match, right? So to do this one, we have to basically talk about the horizontal motion. So in the horizontal motion, here they've spoken about the distance has been provided, 22 meters. And out of the 22 meters, we know that horizontally an object's velocity doesn't change. It's a constant velocity. So we use the basic formula of distance, which is speed into time. So from here we can find the time, and the time would be displacement by its speed, horizontal speed. So horizontal speed is which one? This one, u cos 35, right? This is the horizontal component. So displacement is 22 divided by this one. So we got this one, 1.58 seconds. Time taken to reach maximum height. So because we know the total time, this is the total time to go from here up to the goal, right? But if we wish to know if this ball is maintaining the condition is the ball must be more than 3 meters above the ground at the end. Only then can it score a goal. Because if you watch rugby matches, the post is actually like this. You have to clear this horizontal bar. You have to clear this horizontal bar to score, right? So what I did, I basically divided the journey into two parts. First, I found the time taken to reach the maximum height, meaning this height. So I found the time. So the initial velocity was u sine 35, which is 17 sine 35, and the final velocity, because it reached the maximum height, would be 0, and the acceleration would be minus 9.81 because it's acting against gravity. So we get 0.994 seconds. So this is the time taken for the ball to reach the maximum height. Then it starts to fall. After reaching the maximum height, it says what? The ball reaches a maximum height of this much before returning to the ground. So from here, it starts to fall again. So that is the second part of the journey. So time left to fall is 1.58. This is the total journey's time, and this is the time taken to rise. So this is the time that is left. So if we use this value and we talk about the journey's part where it falls from here, it starts to fall from here. So here its initial velocity is 0. So that means u is 0. And that is why if u is 0, we can make this entire thing 0. And that is why we can simply say half AD square is equal to S. So A would be 9.81 because now it is falling with gravity. And the time left to fall would be the time it has from here, top highest point, up to reaching the rugby post. So we put this time here and we got this value. So this is how much distance it has fallen from the highest position. So what was the highest position? 5 meters. Out of 5 meters, it has fallen 1.68. So how much is its length? How much is its distance above the ground now? 3.32. So it's maintaining the condition that it has to be 3 meters above the ground for it to be a goal. So that means this is actually a goal. Then number 14. Show that the speed at which the seawater is projected from the pipe is about 37 meters per second. This is a basic mathematical problem. So first, if we wish to find the speed, we have to basically find the volume of the water first. So volume is what? Mass by density. Mass of the water is 300 kgs and density is given 1030. We found the volume of water that is ejected every second. See, this is the amount of mass ejected every second. So this is the volume ejected every second. So we know the volume that is ejected every second. And if we wish to find speed per second, this is from mathematics. It comes in basically calculus. If we wish to find speed per second, sorry, not speed per second, more like how much is pumped per second, how much distance is moved per second. So we basically find the speed, right? So volume, if you divide the volume by the cross-sectional area, what do we know? We know that, let me just write it over here, that, volume is actually what? Volume is cross-sectional area multiplied by length. So if I say I find the length is what? Volume divided by cross-sectional area. So this length would give me the length. But if I say how much length is covered per second, that will give me the, that is something I can get from volumes per second divided by cross-sectional area. How much volume is ejected per second divided by cross-sectional area. If I do that one, I'm going to get the length that is being cleared every second. Length per second is basically speed, right? So volume is mass by density. I found that. Cross-sectional area of the pipe, it has the diameter of 10 centimeters. So first we convert the diameter into radius, right? Pi r square is, the cross-sectional area of any pipe. It's a circular shape. So from here I found the cross-sectional area. And because, like I said, that if I wish to find the how much speed it's at which it's being ejected, speed is basically length per second. Speed is length per second. So I know, if I wish to find the length, I have to divide the volume by the cross-sectional area. That's what I did. I divide the volume by the cross-sectional area, and because it is mentioned that the volume is per second, so that means the length that I get is going to be per second, and length per second automatically gives us the speed. So this thing automatically gives me the speed, which is again shown to be approximately 37. So our answer is correct. The next one is determine the rate at which the momentum of the sewer is changed by the pump. So momentum is what? Rate of change of momentum means what? Force, basically. Force is rate of change of momentum. So the unit should be in Newton. And rate means per second. So we can see in the question's first part, it's mentioned directly that it's happening each second. The mass that's being pumped out each second. So the time is already 1. So we don't have to bother about the time. The only thing that we have to bother about is the change of momentum at the top. So change of momentum is how much? Final momentum minus starting momentum. Final momentum was, here the final momentum was what? Final velocity was 36.9. So we put it here. And the initial velocity was how much? They have said initially stationary. So it's 0. Okay. Then projecting water from the pipe causes a force to be exerted on the pump. Explain the relation of the force on the pump. So this is basically Newton's third law of motions, pair forces. So if the pipe is applying a the water is being pushed out by the pump. That means the pump is pushing the water forward. And when the pump pushes the water forward, the water automatically pushes the pump backwards according to Newton's third law of motion. So that is what's been talked about here. Then initially the pump is turned off and the fireboat moves forward. So what happened here is the fireboat moves forward initially, and it moves at a constant velocity, meaning what? That the forward force by the engine is equalized by the backward force from the drag force. Now what happens is, then they start pumping the water forward. So when you pump the water forward, automatically a force would be applied to the back. That means what? If a force is applied to the back, that will mean what? That will mean there is now an additional backward force. So the net force will now be pointing to the back. Now the net force will be pointing to the back. And if net force points to the back, that means what? That means it causes deceleration. That is what happened. That's why it slowed down. And then again it maintained the constant speed. Why? Because if you have decelerated, that means what? That means you have slowed down. And when you slow down, what do we know? Drag force depends on velocity. If you have slowed down, your drag force automatically decreases. If drag force decreases, that means the force which is acting backwards has decreased. That means what? That means the engine force and the backward force will again balance, meaning what? Now they will again move at a constant velocity because the net forces have balanced. The net force is 0 because the forces have balanced out. Number 15, star mark questions require you to be very, descriptive. You have to describe everything as much as you can. 6 mark questions. These star mark questions are almost always 6 marks long, right? So you have to describe this 3 stages, right? So the first stage, they have said the jumper is in free fall until the cord starts to stretch. Free fall means what? It's falling at acceleration due to gravity. So that's why I said at free fall, the velocity increases by 9.8 meters per second every second. So because it's at free fall, meaning what? It's acceleration. So if it's accelerating, that means what? The kinetic energy increases because kinetic energy depends on velocity. And if the velocity is increasing, it's definitely acceleration. Okay, that's what I wrote here. Then they have said the cord is stretching until the acceleration of the jumper decreases to 0. Acceleration decreases to 0. If acceleration decreases to 0, meaning what? It means that the net force has become 0. Acceleration becomes 0 when? The net force is 0, right? And if the net force becomes 0, what do we know? The velocity becomes constant. Acceleration 0 means the velocity has become constant. That means the kinetic energy also becomes constant, right? Acceleration falls to 0 means kinetic energy is now constant. So why does the acceleration fall to 0? I mean, previously it was at free fall. Then why did the net force become 0? Why did the net force become 0? Because now the force is used to pull the person upwards. Where is the force coming from? From the tension in the string. That's what I wrote here. This happened because the work was done not only to increase the kinetic energy, but work was also done on the cord, right? So this work done on the cord is actually pulling the person a bit towards the top. right? So this tension, this force is basically responsible for decreasing the net force to 0. Okay. The velocity, the last part is the cord continues to stretch until the jumper is momentarily at rest. So the person has come to rest, meaning what? Previously the acceleration was 0, but even if the acceleration was 0, the person was still moving at a constant velocity. But in the last stage, no more constant velocity, is actually at rest. So the person actually comes to rest, meaning what? The kinetic energy is now 0, because velocity is 0, meaning kinetic energy is also 0. Why does this happen? This is because the work done on the cord is equal to the work done by gravity. So work done by gravity is done which way? To the, in the downwards direction, and work done by the cord is done in the upward direction because of the tension. So these two, work done's balanced out, and we know work done is it's a vector quantity, so they cancel out. That is why the kinetic energy became 0. So you have to describe all the steps, all the different aspects of the question. That is how you'll score the 6 marks. So these star mark questions are very crucial. Then this one, state a suitable measuring instrument to measure the diameter of the sample. So if you want to measure the diameter of anything in physics, just simply go for micrometer screw gauge. Straightforward. Then determine the Young modulus of the sample. So if you wish to find the Young modulus from a stress strain graph, you always have to take the gradient of the linear region. That's what I wrote. So I found the gradient, normal y2 minus y1 divided by x2 minus x1. Then sample broke at point B. So this is the breaking stress, right? B is the point where the breaking stress takes place. So determine the force required to break the sample. So the stress is 1280, right? The breaking stress is 1280, and we know stress is force by area. So from here I found the force. So force is area multiplied by stress. So stress I already know from the graph, 1280 megapascals, and the area I found from where? Area I found using the diameter. Diameter will be converted into the radius, pi r square, right? Because the cross-sectional area is always a circle, so pi r square, right? That is how I found the force. Then show that the area under this graph represents the work done per unit volume in stretching the sample. So stress versus strain. Area is what? As we can see, it's a triangle. So half into base into height, half into strain into stress. So what is stress? Stress is force by area. Strain is what? Extension by original length. So if we now break them down, we can say half into force, and in the top part, the numerator is what? Force into extension, and denominator is what? Area into original length, right? So what do we know? Half Fx. Half Fx is what? Half Fx is actually, the work done. Whenever we take force versus extension graphs, half Fx is the area under the graph. If we took, let's say, force versus extension graph, half Fx would be the area under the graph. So half Fx is what? It's the elastic potential energy, right? So half Fx is the work done, and divided by AL. AL is what? Cross-sectional area into length, which is what? Volume. So that is why we can prove that half Fx, it's the elastic potential energy, or we know that any sort of energy is basically work done. Whenever you cause something to gain elastic potential energy, that means work is being done on it. So whenever something gains elastic potential energy, that means work is being done on it. That is why half Fx we can say as work, and AL is volume. So work by volume. So we have proved it, that this area actually gives us work per volume. Then they told us estimate the amount of work required to break the titanium alloy sample. So using the area of this graph, we have to find the work. So if I wish to find the work, I already know the work done per unit volume from the graph. If I find the area of the graph, I will find the work per unit volume. Okay. So first I find the area. So area is what? Basically this entire shape. This is an estimation, of course, because this is not a proper shape. It is a proper shape up to 1000, then it becomes bent. So let's say up to 1000, take it as a triangle. Then I take this much as another triangle, and then I take this as a trapezium. So if I add all of these, I'll basically be overestimating it, because as you can see, this part is actually extra. This part is extra, but still it's an estimation, so it's no problem. So that's what I got. I added them. So the area that I got is actually work per volume, but I wish to find just work. So if I wish to find just work, I have to multiply the volume with the area. So volume, what is the volume? This is basically, if you look at the question carefully, it says it has a diameter of this and an original length of this. So it's a cylinder. This sample is actually a cylinder because it has a length as well as a diameter. So cylinder's volume is pi r square h. That's what I wrote here. Using this volume, I put it here. I found the work to be 511 joules. So such questions, they will give you a range, because these are estimation questions. Estimation questions will always give you a range. So you don't have to worry about, if your friends get an answer which is a bit different to yours. They will give you a range. Within that range, if your answer falls, you're perfectly fine. Number 17, show that the stiffness of the spring is about 2 newtons per centimeter. So this is the formula. Force is stiffness constant in extension. So K is F by X. F is 15 and the extension is 8. Okay, so that is what we get, 1.87 newtons per centimeter, which is approximately 2 newtons per centimeter. So answer is shown. Then calculate the value of theta and the extension of the spring in the force meter. So if you look carefully at the question, there are two springs, one here, one which is connected to the force meter, and the other which is connected to the stand. So the force P is actually the force on one of the strings, and the force F is the force on the other string. So we have to basically find the extension of the spring which is being applied with the force F, right? And we have to find the value of theta as well, this theta. So we have to resolve it horizontally and vertically. So if you resolve it horizontally, we can see that this horizontal component of this force F is balancing the force P to the right. So F cos theta is equal to 8.5, and the vertical component of this force F, which is F sin theta, is balancing the weight of this mass, which is 0.55 kg. So we have to resolve them. So that's what I did. Okay, and after resolving them using 1 and 2, if I divide 1 by 2, what do I get? F and F cut off. So sin theta by cos theta gives us tan theta. From there I could find theta, and to find F I have to go for magnitude, the formula to find magnitude. So which is the square of the two components. You add the square of the two components and you put a square root over it. So why do I do this one, F sin theta square plus F cos theta square? Because if I take F square common in these two things, let me just point it out to you. So if I take F square common in these two things, F square, we get what? Sin squared theta plus cos squared theta. And we know from pure mathematics that sin squared theta plus cos squared theta is basically 1. That is why we get F square, right? So this internal thing is actually giving me F square, and if I put a square root over it, I get F. So that is why I put this formula into use. So from here I found the value of F, and after I found the value of F, they are asking us to find the extension of the spring in the force meter. So we have to find the extension of this spring which is applied with the force of F. So we know the formula, F is equal to K into X. So we found the extension F by K. F is 10 Newton and K is something we already found here, 1.875. Put it here, we got it. I believe this is the last question. Yeah, this is the last question. So show the upthrust the oil exerts. So upthrust is what? Before we go into the upthrust, we have one part left here. So here they're telling us that the bead is released and moves upwards. The bead is moving upwards. Okay, so the bead, if it moves upwards, the drag force is going to act downwards, because drag force always opposes the motion. So if its motion is upwards, that means its drag force is going to be downwards, right? And also its weight acts which way? Downwards. Weight acts downwards always. So here the upthrust they have already labeled, and drag force acts downwards because the object is trying to move upwards. It's going to oppose the motion. That's why drag force is downwards, and weight is always downwards, right? Then upthrust is what? Weight of fluid displaced. So weight of fluid displaced is what? The mass of the fluid multiplied by value of G, right? What is the mass of the fluid? It's density multiplied by volume. What is the density of the fluid? 930 given. And what's the volume of the fluid? Volume is what? This fluid, as you can see, this bead, the fluid volume which has been displaced is basically the volume of the object, right? Basically this is the water displacement method, right? So whatever much water you displace is actually the volume of the object itself. So whatever the volume of the object is will be the same volume of water which has been displaced. So if we find the volume of the object, we will directly get the volume of the the oil which has been displaced. So that's what I did. 4 by 3 pi r cube, right? The r is half of the diameter. I put it here. So from here I found the mass of the fluid, and upthrust is what? Weight of the fluid. So mass of the fluid multiplied by G, I got the upthrust, which is 3.06 into 10 to the power minus 4, which is approximately 3.1. So our answer is shown to be correct. The next one, Stokes Law shows how the viscous drag is related to its velocity through a fluid. Stokes Law is only valid if the bead is moving sufficiently slowly through the oil. Say the reason for this condition. So if something moves fast, we know that if we put on the tap water slowly, it has laminar flow. But if we put on the tap water fast, it becomes a turbulent flow. So we have to make sure that the flow is laminar At higher velocities, the flow becomes turbulent. If the flow becomes turbulent, it's not going to follow Stokes law. So it has to be laminar, right? That's why we have to make sure that the flow is laminar, and that's only made possible with the low velocity. Last question of this paper, they're telling us this formula is given to find VR, which is a critical value, which is a reference value. First we find VR, then using the formula 10 into viscosity of oil, which is given 4.90 into 10 to the power minus 2, divided by density of oil, which we know from the question 930. Diameter of the bead was, that is something we also know from the question, 4 into 10 to the power minus 3 meters. So using these values, I found VR. Then we combine, now that I know the value of VR, they are asking us whether it's valid. They're telling us for Stokes law to be valid, the speed of the bead must be less than VR. So whatever value of VR we found, the value of the bead itself, actually the actual value of the bead in the question has to be less than this reference value. So we first find the velocity of the bead. So how do we do so? We make use of this equation. So what can we see here? The upthrust is the upward force, and the weight and the drag force are the downward forces, and these are equal. Why? Because they're telling us it's moving at a constant velocity, meaning what? Upward force is equal to downward forces. So upward force is upthrust and downward force is drag force plus weight. So it's U is equal to D plus W. Okay, so D is what? U minus W, and U is something we found here, 3.06 10 to the power minus 4, and W is the weight. And the weight is what? The weight is given here. Weight of polystyrene bead given in the question. This is the weight. So the drag force comes to this much. And what is the formula for drag force? The Stokes force is what? 6 pi r eta v, right? Eta is the coefficient of viscosity, which is given here, 4.90 into 10 to the power minus 2. So we have to find the terminal velocity, right? Terminal velocity comes to this much, right? We put it in everything here. This is the value of D divided by 6 pi. R is also given in the question because the diameter was 4 into 10 to the power minus 3. Radius should be half of it, 2 into 10 to the power minus 3. And eta is also given here. So we all use all of these and we get the terminal velocity to be 0.16. And to follow, for the Stokes law to be valid for this question, we have to make sure that the terminal velocity is actually less than VR, which is 0.1317. And as we can see, the velocity that we are getting is actually more than the VR value. So that means in this question, it's not following Stokes law. So the law is invalid for this question. Okay. So that's the last of this. So this was the last question of the paper. Thanks for watching the video.